For this afternoon and tonight, a significant winter storm, including heavy snow with blowing and drenching.
Hello and welcome to the Snow Brains podcast, where it's my job to interview the most intelligent people in the snow sports industry and pass their fascinating knowledge on to you, our listeners. I'm your host, Miles Clark. I'm a professional free skier, a mountain guide, an Alaska heli ski guide, a UC Berkeley molecular cell biology graduate, the founder and CEO of Snow Brains, and I just got back to Lake Tahoe, California, after having been gone for 10 months. I'd completely forgotten just how gorgeous this place is. 3 days ago, we climbed up and skied down above the lake, and I couldn't help simply having my mind blown again and again as the lake changed color and shape with the many moods of the day. Deep, sunlit powder, old friends, stellar skiing, and shit-eating grins marked the day. There's nothing quite like Lake Tahoe. Thanks, California. Today's episode of the Snow Brains podcast is brought to you by Club Med. Escape to one of Club Med's more than 20 mountain resorts in Europe, Japan, Canada, or China, where you find world-class skiing and snowboard terrain, exceptional service, and endless adventure. With their all-inclusive packages, you'll get everything you need for an unforgettable ski vacation, all taken care of. Lift tickets, ski and snowboard lessons for all ages and ski levels, gourmet meals, lively après-ski activities. Visit www.clubmed.us, call 1-800-CLUB-MED, or call your travel advisor today. My guest today is Dr. Daniel Swain. Dr. Swain is a climate scientist in the Institute of the Environment and Sustainability at the University of California, Los Angeles, and holds concurrent appointments as a research fellow in the Capacity Center for Climate and Weather Extremes at the National Center for Atmospheric Research. Daniel studies the changing character, causes, and impacts of extreme weather and climate events on a warming planet, with a particular focus on the physical processes leading to droughts, floods, and wildfires. He holds a Ph.D. in Earth System Science from Stanford University and a B.S. in Atmospheric Science from the University of California, Davis. Hello, Daniel. Welcome to the show. Thank you so much for being here. How are you, man?
Thanks for having me. It's you caught me in one of these windows where there's just a lot of crazy stuff going on, but it's always good to have some time to slow down and talk about snow.
I love how crazy your life is, and I like that you like to talk about snow. That's great. And so you told me a little bit about before the show, but when was the last time you went skiing?
Usually the answer would be a long time ago because I'm not a big skier, but actually in this case, last week because I was in South Lake Tahoe for Operation Sierra Storm. One of those very snow-centric events that is sort of an educational event for broadcast meteorologists out there. There's a couple of these. They would do one in Steamboat Springs. They do another one in South Lake Tahoe. And this year I was in the South Lake Tahoe version where there was very little snow actually at lake level. You go up to 10,000 feet at the top of the Heavenly Chairlift. It looks quite a bit different, but some spring skiing conditions last week in late January in South Lake Tahoe, I think, is sort of what it felt like then.
It happens so often here. We often call January Junuary here in Tahoe. So, because I'm in North Lake Tahoe right now. So, yeah, you experience it firsthand. Well, to start, Daniel, I'd love to hear your quick and dirty life stories. I usually say a 3-minute life story, but if it goes longer than that, that's fine. I think it's a really cool way to connect with people and figure out where they're coming from and where they're headed.
Well, I was born in San Francisco, grew up in the Bay Area, San Francisco and the North Bay, San Rafael area. Got my undergraduate degree in atmospheric science at UC Davis, so moved over to the Central Valley for a bit. Then down to Stanford, down the San Francisco Peninsula for a Ph.D. in Earth System Science. After that, Los Angeles, postdoc at UCLA, and now a climate scientist since then at UCLA as well, along with a joint appointment with the National Center for Atmospheric Research, which is here in Boulder, Colorado, where I am currently speaking to you from and where I currently reside. So I've done a bit of a circuit, still very strong California ties, and of course, very strong Western U.S. ties, broadly. But in this space, sort of, I've spanned sort of weather and climate disciplines. So I am both a meteorologist and a climate scientist, and there aren't that many folks who can say they are truly both of those things, because as is the talk of Twitter today, these are kind of siloed disciplines. And so you get a lot of people who know about climate change or people who know about the weather. And surprisingly, despite the fact it's all the same atmosphere with all the same physics and thermodynamics, sometimes there's a little bit of an artificial separation there. So long story short, I spend a lot of time spanning that gap, speaking with the public. My current role as a climate scientist at UCLA is a very public-facing one. So you've probably seen me on the news, on social media, in a documentary, wherever it is. I spend a lot more time on screen than I ever thought I was going to.
That's very cool, man. Congratulations on all the success. And I have been following you for quite a while, and I love what you do. I didn't realize that is the overlap there, a climatologist and a meteorologist. And you seem to be drawn and have an affinity for extreme weather and like these big events that are so interesting. And I feel like we just kind of went through one of those on the West Coast and the Western US. So I'm really excited to dig more into your brain and see what your perspective is and what the data says. Really, because that's something that we really don't have access to as public people. So I guess my first question is, you told us what you study. What do you hope to accomplish with your studies? What is your goal?
Well, part of it is understanding, as you mentioned, how extreme weather events are changing in a warming climate, both how they are now, how they're going to be in a climate that is warmer and more energetic in some ways than it used to be, and also how that's different or not so different from what we're used to historically, and what that means for all of us in terms of how we live our lives, how we adapt to climate change, how we build our infrastructure, how we plan for the future in a variety of ways, and hopefully in doing so avert some future problems, head them off at the pass, so to speak, before they become big problems, or at least to the extent that we can prepare for the kinds of big bad things that we know can sometimes happen, whether that's wildfires or floods or droughts or things in between.
Terrific. Yeah, I think that's a fascinating place to be. And because I think there are, we're not doing a lot of things right, probably. And so it'd be really interesting to see what the solutions are. And I guess, but the elephant in the room, I think already is, what does science say about anthropogenic human or human caused climate change on Earth? What does the data say?
Well, it's here. The Earth is warming. There is absolutely no doubt about that, and it's warming in a way that is genuinely rapid in the context of all the Earth history that came before. We have carbon dioxide levels in the atmosphere that are higher than they've been in hundreds of thousands of years, and we're on a warming trajectory unlike any that we've seen since really the era of human civilization. And so, we're on this path. We know that the warming is happening. You just have to look at thermometers and ice sheets and the snow lines to get that far. And we know that the essentially all of the warming we've seen is due to the accumulation of heat trapping greenhouse gases in the atmosphere due to human activities, because we tried all the other hypotheses for things that might be causing the warming, and none of them work out. But this one fits essentially perfectly with the pattern of warming spatially on Earth that we see, with the vertical profile of the warming, which parts of the atmosphere are warming faster than others, with the rate of change that we're seeing. All of these things, the fingerprint puts it squarely on those heat trapping gases in the atmosphere. And that's why it's anthropogenic, human caused, because we're the ones who put those greenhouse gases up there, and we're continuing to put them up there at a rate that has never been higher than it is right now. So that's the good news and the bad news, right? It's the bad news because it's us and we're still doing it. And so we're going to see more warming and more increases in extreme events and, warmer temperatures that push that snow line higher and higher up the mountain. But it's good news because it is ultimately something that we have done, and we can also fix it. If this were some exogenous alien laser beam causing the Earth to warm, we'd kind of be screwed, right? That would actually be really bad news, because what the hell would we do about that? But
Yeah.
It really plays into your pessimism versus your optimism about society and human nature. It's a problem that we cause, which is good in the sense that it means we can fix it, but it's bad in the sense that we haven't really begun to bend that curve as meaningfully as we would need to slow and halt the warming sooner rather than later. So we're still on a path for a lot of additional warming, and therein lies the challenge.
Therein does lie the challenge. And when you speak about, as skiers and riders in the Western US, we do see, and I think the East, we see the snow line going up. Last night it was raining till I went to bed, and luckily by the morning it snowed a little bit here in Tahoe. So I guess just to open this can of worms, how is the climate changing in the Western US?
Well, as you might expect, if from a term that's called global warming, it is getting warmer. Temperatures are rising, and I think what's maybe a little bit less intuitive is that temperatures aren't rising at the same rate everywhere at all times of year. So the warming itself is a function of where you are on Earth. So in general, the continents warm faster than the oceans. In fact, about 50% faster than the oceans. So it's quite significant. The Arctic is warming 3 or 4 times as fast as the rest of the world.
Wow.
So that's dramatically faster than the rest of the time. And it turns out that cold places and cold seasons generally are warming faster than warm places and warm seasons. So this is all sort of squarely in the territory of affecting the cryosphere, the frozen world, ice and snow, on planet Earth, because it is precisely those places where ice and snow is most prevalent where the warming is happening the fastest and the most prominently. So the Arctic, the high elevations, and the winter in each hemisphere. So, we see that this is warming. The West has a lot of topography, right? We have coastal areas, we have the highest mountains, in North America. So there is an elevational gradient of that warming. And in many cases, the warming is faster, the higher you go up the mountain. And also, in a lot of cases, the warming is faster at cooler times of year. So, some of what we're seeing is that some of the cooler times of year have warmed faster than the very hottest summer days. Those are getting hotter too, but not quite at the same rate as some other times of year. And of course, all of this matters a lot in a region that is highly snow dependent, both for its ecology, its hydrology, and of course, its ski seasons. But that snow, that mountain snowpack throughout the West is important for almost every reason you conceive of. You can conceive of, hydroclimatologically and in terms of society and recreation. A lot of that water, that's on the ski slopes in the winter, the people, the resorts depend on, people who enjoy skiing depend on, then eventually becomes water that enters watersheds that is the water that you end up drinking throughout the summer and the autumn months downstream. It's what flows into reservoirs to a large degree, all across the West. It's that melted snow that becomes the water that you and I and really everybody in the West uses for all the purposes that we use water for, which is, a heck of a lot of things. And it includes industries, it includes agriculture and factories and everything. So that snow is a big part of the water that matters out west for a bunch of reasons. And so the challenge is that if that water is going to be arriving differently than it used to in the 20th century, when a lot of it came as snow, if an increasing portion of it comes as rain rather than snow, or falls at later in the year or melts earlier in the season, then that's really going to affect not only the mountain hydrology, but also all of these water systems that we've built to capture snowmelt preferentially if there is either less snowmelt or if it's happening at a different time of year, increasingly out of alignment with when we actually need the water during the warm, dry summer months. So all of that is shifting in a warming climate, along with some other things too. We are seeing more extreme summer heat waves, and we are seeing more extreme winter precipitation events in some cases, and we're seeing more extreme wildfires all around. So it's not just getting wetter, and it's not just getting drier out west. Both things are happening, and in some cases, it's happening in the same place. And this is something that I increasingly call hydroclimate whiplash. This notion that even if the overall amount of precipitation is staying somewhat the same in some regions, more of it's falling as rain versus snow. So you're getting more of those transitions between liquid and solid states, and you're seeing more potential evaporation on the one hand, but more potential precipitation on the other hand. So you kind of see these increasingly wide swings of the pendulum between really wet conditions and really dry conditions in a warming climate. And as you mentioned in the introduction, we've seen that in spades in recent years out west.
And I think it's so interesting too, because one of the things that I've talked to some other climate folks about is some of the estimates are we're getting somewhere around 30 less freezing days in Lake Tahoe area here in California, which is huge for us as skiers. But then you think of it also as you were reflecting on our drinking water and farming and all that. So we're also getting that frozen reservoir that we have here in California specifically. And I've heard that something like 70% of our drinking water in California comes from the Sierra Nevada mountains. So could you speak a little bit to just the frozen reservoir? Because that's kind of what you were alluding to and how important that is in the Western US.
Yeah, I mean, you mentioned that there's been in some places a 30-day or more increase in the number of non-freezing days where it doesn't get below freezing
Mhm.
in parts of California's mountains. And that is hugely consequential because California has perennially been, even in a cooler 20th century climate, kind of on this cusp, right? Where one of the reasons why the Sierra Nevada gets so much snow sometimes, I mean, just these enormous volumes of Sierra cement, really heavy, wet snowfall, is because a lot of it falls at temperatures that are just cold enough for it to be falling as snow
Mhm.
rather than rain, which is great if you want to accumulate frozen water because the amount of water vapor in the atmosphere increases rapidly as temperatures go up. So the closer you are to freezing, the more moisture you can actually squeeze in per volumetric inch of snow, the more water equivalent you can get as you butt up right against freezing. If it's snowing at 0 degrees Fahrenheit, there's not a lot of moisture in it. It's nice fluffy powder, but you're not getting as much water accumulation. Right up at 32, it's that sweet spot in terms of water accumulation. But the problem is if you go beyond it, if you continue warming another degree or two past 32, then all of a sudden you're on the wrong side of the freezing line. And that is a very powerful threshold in nature, 0 degrees centigrade, 32 degrees Fahrenheit, the freezing point, because water is either liquid or solid, depending on which side of the line you go. And really, it can be just a fraction of a degree on one side of it or the other, really dictates whether that's falling as liquid rain or solid snow. And South Lake Tahoe, for example, at 6,200 feet, somewhere around there elevation, has historically been kind of just on the cold side of that freezing line for most of the 20th century. But in the last decade or so has increasingly been just on the wrong side of the freezing line, half a degree or a degree or two too warm. So a lot of these events that would have 50 years ago been heavy snow have just been heavy rain or slop that doesn't really accumulate. And you can imagine this is even more pronounced as you go a bit farther down the mountain, 4,000 or 5,000 feet. This is even more pronounced. And the challenge in California is that there is land, of course, at higher elevations up at 8, 9, 10,000 feet, but it is rarefied air. Just think of a classic mountain shape, right? It gets narrower as you get closer to the top. So there's less area above a particular elevation. And so if the snow line goes up, it's not just that you're losing this uniform amount of snow, but you're losing it as the amount, sort of this rate of snow accumulation at a nonlinear pace because as you go up the mountain, it gets rapidly, rapidly narrower. So this
Mhm.
all has implications for California's water infrastructure because it's kind of predicated on this nice, convenient, gradual snowmelt, water release through the spring and summer months historically. So our reservoirs are not designed to capture huge winter storms that dump a ton of rain and to store all that rainwater. They're designed mainly to pass most of that rainwater through, let it go on downstream, but to be ready when that snow melts somewhat gradually in the warmer months, spring and summer, to capture that water because it's a much gentler, for the most part, rate of inflow. And then, you have this water that's becoming available and entering the reservoirs as snowmelt right when you need it, when it stops raining, right? In the spring and summer and into the fall. So it was a really good system historically. And so the challenge there is that increasingly you have a snow melt season that's out of alignment with the way the water systems were designed. So if you're getting either snow melt that's occurring earlier in the year or there's just less snow to melt in general, that nice convenient water release right when you need it isn't necessarily happening, in the quantity or with the timing that you would want for that system to operate effectively. So that's one of the key challenges with, warming temperatures in a snow dependent, regime is that it really just messes a lot of things up in terms of the systems that we've put in place, but also in terms of ecosystems, and the forests that are in the mountains you have a longer season where you don't have snow cover on the ground, for example, and increasingly, at higher elevations. So some of these places are becoming drier and more fire susceptible because, if in the 20th century, most years you had a nice blanket of snow on the ground into May or even June, sometimes July during a cooler, wetter year.
Mm-hmm.
And now those places, May, June, and July are warm months where you don't have any snow on the ground, and that's just water getting sucked out of the soil. That makes for a pretty big difference.
Huge difference. And I love what you said about the mountain shape. I explain it as the mountain's basically a big triangle. So in Bariloche, Patagonia, Argentina, where I ski a lot in the summertime, the bottom of the mountain is the bottom third of the mountain usually doesn't have snow. So you got to ride the chairlifts up and down to get over that. And when that bottom of the mountain doesn't have snow, it's the bottom third of the mountain that doesn't have snow, but it equates to more than 50% of the actual terrain of the mountain. So when you lose that lower elevation snow, you lose so much snow and so much terrain. So as selfish skiers and riders, we're frustrated by that. But then when you play that forward into, drinking water and how we have our reservoir set up and all that, it has much bigger consequences that are more important. But both systems are affected. So there is something there to be concerned about. How do you think, looking forward and knowing what we know has happened in the recent past with the Western U.S. climate, how do you think the climate is going to change in the Western U.S. in the next 20 years, even the next 50 years?
Well, next 20 to 50 years, it's going to keep getting warmer. We know that as much warming as we've seen to date, we're currently on track, with current climate trajectory to about double it still.
Whoa.
That's not it's a significant amount of warming already. And now, think 2 times that. And the challenge is that it's not necessarily a linear increase in the impacts. So you don't necessarily think, oh, you double the warming, you double the impacts. It's probably a lot more than that, partly for all the reasons we've just been talking about, in that there are intrinsic thresholds in these systems, right? Like it really does matter exactly whether you're slightly above or slightly below freezing. And so, you double the warming, you more than double the amount of the time or the amount of area that's perennially above that freezing point and on the wrong side of the snow line. So there's that element to it. There's the tipping points in ecosystems. You start to lose some of the stability of the forest that we have. We've already seen this in recent years, in some parts of the West where we've seen, and in South America, where we've seen some forest die-offs, in the mid-latitude forests in the mountains because they've been so dry and warm. But I think that, what we will also see is, as I mentioned, these increasingly wide swings between really dry and really wet conditions. And this is something that's a little bit different, I think, than some folks have come to assume, which is that either the climate is just going to get perennially drier. And that's not necessarily the case in everywhere. In fact, it's really not the case in a lot of the West. It may get drier on average in the deep Southwest. So if we're talking Arizona and New Mexico and the lower Colorado basin, the reality is that probably is getting significantly drier on average, and we're already starting that process. But California is a bit different, and the Pacific Northwest is different still, and much of the Rockies. North of the lower Colorado basin, I think, are in a different story, where it is, of course, getting warmer in all of these places. But, in some spots like the Pacific Northwest, it might get a little bit wetter on average, for example, as it gets warmer. In California, it might not necessarily get wetter or drier on average, but we're going to see more of the really wet years and more of the really dry years. So more of these increasingly wide swings, this hydroclimate whiplash. And I think that's going to translate, from a snow perspective. There's a lot of evidence we're going to see years more like, 20, I think it was 13, 14, where there was that was the year when there was effectively no snow, even at peak winter, in the Sierra Nevada and some other, adjacent mountain ranges. We're going to see years where there is effectively no snow at all. But we're also going to probably still see some winters where there's huge amounts of snowfall. And I think that what's going to happen is that as the average amount of snowfall decreases, it already has, and it's going to continue to decrease, we'll still see some of these really big snow years. And what's interesting about this, and in really big individual snow years, and also just really big individual snowstorms, even in years that aren't so great otherwise. And that becomes kind of this interesting challenge where a lot of the really manageable light to moderate snowfalls kind of go away. But what you're left with is you still get these super huge dumps of massive amounts of snow at the higher elevations, even in a warming climate. So how does this work? There's actually two things going on. As we were talking about earlier, and this is, I think, is probably pretty intuitive to most folks who think about snow, as it gets warmer on average, right? All else equal, you get less snow because it's just you're on the wrong side of the freezing line. But there is that exception to it, which is that as it gets warmer, there's also more moisture in the atmosphere. So to the extent that you are still on the right side of the freezing line, which is to say below freezing, even if you're just a little bit below freezing, you actually have more moisture to work with in terms of how the quantity of the snow that you get and the moisture content of that snow. So at high elevations, I mean, we're talking like 8, 9, 10,000 feet. We may not see huge decreases in future snowpack. And we actually, at at the top of the heavenly chairlift, you might actually see more snow in the future, or at least more snow water equivalent in the future, because it's getting warmer up there, just like it is everywhere else. But warmer there still means below freezing. It's just less below freezing than it used to be, but there's more moisture. And so you get these incredibly heavy snow events, at wet, heavy snow events at these really high elevations. And that happens to a lesser extent in years, at lower elevations in years that happen to be a little bit cooler. But we kind of have this tension between large decreases in average snowpack, typical snow events sort of disappearing and becoming rain events or going away entirely, but these really extreme snow events still occurring, particularly at higher elevations, and maybe even becoming a little bit more intense at the very highest elevations as temperatures get warmer. It's a little bit counterintuitive, but there are a couple of places in the world that might see heavier snowfall events in a warming climate. One is the Arctic Ocean, which again is the fastest warming place in the world. Why might it get more snow? Well, you take the Arctic and add 10 degrees and it's still pretty cold, but you got a lot more moisture. And the same thing is true up at 9, 10, 11,000 feet on some of these mountain peaks in the American West, and probably in a lot of places in the world where you're not yet temperature limited, even if it's a few degrees warmer, where you're just getting more moisture. So I think that there's this weird, the headline really is we're losing snow, and there's going to be less snow, and the snow lines are going to be creeping higher up the mountains. But that there is this interesting side narrative about how the very most extreme snow events, especially at high elevations and in cold places, might stay just as extreme or get even more so. And so that snow whiplash, is a very real thing that we might see too. And I think we've seen it, just compare the last few years in California in terms of snowpack. I mean, last year was an incredible snow year. This year is a terrible snow year. We've seen like some of the highest and the worst snow years on record in the last decade, I think, on multiple occasions in California, which is very much something I think we should expect to continue.
Because anecdotally, as skiers and riders in the West, that's what we're seeing. That's what we're feeling. Is one of my questions here is essentially saying what you just said to me. As a skier and rider, it seems like 20, 25 years ago, most winters were somewhere around average snowfall. And of late, it seems like we get these huge years and then these really big drought years. And it sounds like you're saying the data supports that feeling that we see as out, boots on the snow people.
Yeah, I mean, an overall decreasing trend in snow at most elevations, but the big years are staying big. And so those swings of the pendulum are becoming greater because we're keeping those big snow years, but we're also adding in a lot of really terrible snow years in between them.
I'm going to make the step and say the warming is caused by this human-caused climate change, which is leading to this erratic behavior and a lot less snow. And I think that's another headline that you brushed right past, but is huge for us as skiers and riders, is we are seeing consistently less average annual snowfall year over year. Terrifying.
Yeah, and that's the part that unfortunately is really just going to be an increasing reality. And I think that this is a real challenge for really anybody or anything that is snow involved, right? Because it makes it difficult even to plan year to year, to operate to reservoirs, to operate a ski resort. If you know that you're getting less snow on average, but you also know that some years are still going to be huge snow years, that make it so much snow that it's even difficult to get up there, or difficult to manage. How do you plan for that? Some years where you're going to say, well, it's January and there's nothing on the ground, so good luck. And then the next year, you have 200 inches on the ground and you're like, oh, sorry, we're closed because, we can't clear the roads. There's too much snow. I mean, how do you manage going back and forth between that? If you live in a place like this, if you operate a ski resort, and then there's the question of snowmaking. too.
Mm.
Now that a lot of these resorts, really all around the world, have increasing capacity to make their own snow, it doesn't help out with the water supply, of course, because they're making it for the runs themselves, and the slopes next to them are still going to be bare if there's no snow.
Yeah.
But from a recreation perspective, it's a mitigation potentially, right, to these
Mm-hmm.
sorts of bad conditions. But the challenge there is you still need atmospheric conditions that are cold enough to make artificial snow. Like, it's still got to be below freezing,
Mm-hmm.
and ambient air temperature to do this. You can't really make snow, if the air temperature is 35, 40 degrees. I mean, good luck.
Mm-hmm.
That's just not how, thermodynamics work. So it helps up to a point, and at certain elevations, it probably is really helpful. But even those sorts of interventions become really hard. If you're down at 6,000 feet, and it's 35, 40 degrees, it does all the snowmaking equipment in the world. It's still going to be really difficult. And I know there's some details there. You kind of actually have to look at what's known as the dew point depression. So you can get away with it a little bit above freezing, maybe if the air is really dry and there's evaporative cooling. But the reality is, it gets warmer, and it does at a certain point get harder even to make that artificial snow too, because you just don't get conditions that are in that favorable envelope as often.
What's your opinion of snowmaking? How do you feel about it? Is it good for the earth? Where are you at?
I don't really know. It's probably it kind of depends. A lot of that water probably ends up effectively getting recycled. So you pump it out
Mm.
of the lake, and it goes through the system, and it sits on the ground, and a lot of it's going to melt back into the ground. Some of it, though, probably is going to evaporate directly. I mean, there is some loss of water, but I think that it's difficult to know, under certain conditions, of what the cost benefit kind of ratio for something like that is. I don't think it's necessarily obviously harmful.
Mm-hmm.
I also would be surprised if it was significantly net beneficial. I have, ecologist friends who might disagree. I'm just not super familiar with the details, but my guess is it's local enough in scale, in the sense that you're really only putting snow on the actual slopes that people are skiing on, that whatever impacts it has more broadly are probably pretty small.
Well, I love that we got into sort of the extreme weather that we experience, especially of late, talking about these huge snow winters that we have, and then these really low snow winters that we have. And so I want to relate this back to the big snow we just had in last year. 2023 was nuts in the West. Alta, Utah got 903 inches of snow, which was a big record for them. And here, even in California, all over pretty much Jackson Hole, everybody had record snow. So I guess we'll do a through line from this question into sort of how we can relate it to what happened in this last year. And with the initial question being, what kinds of extreme weather are becoming more frequent?
Well, in the West, most of the kinds of extreme weather that we experience are becoming more common. So, it's a fairly short list. We know that heat
Mm-hmm.
waves are becoming more common and more extreme. That's probably pretty obvious, as
Mm-hmm.
temperatures rise. A rising tide raises all boats in a certain sense.
Mm-hmm.
When it comes to the wet versus dry extremes, one of the staple of California, and really of Western hydroclimate in winter, are these atmospheric river storms that
Mm-hmm.
bring so much beneficial water, and also sometimes big problems if there's too much water all at once in the form of flooding. A lot of these atmospheric rivers are what deliver a lot of mountain snowpack too. We think about atmospheric rivers as warm and wet, but they're not all that warm. Some of them are actually quite cold, and temperate mid-latitude systems that bring a huge amount of moisture and can sort of be these snow delivery pipelines for the western slopes of all these mountain ranges out west. And so we know that atmospheric rivers are becoming more intense in a
Mm.
warming climate, and it just comes back down to these basic thermodynamic argument. I use the analogy, which I call the increasing or the expanding atmospheric sponge effect, to describe a lot of what's going on here.
Okay, tell us what that means.
Yeah, so you can, and this metaphor, it works pretty well because you can actually replicate it. I've actually done it on camera with two, like one comically oversized kitchen sponge and an ordinary sized kitchen sponge.
Uh-huh.
The basic idea is that, your ordinary kitchen sponge, right? You use it to absorb liquid. And
Mhm.
a larger sponge has at least the potential to absorb more liquid, but it's not going to magically absorb more liquid unless there is liquid to absorb. So this explains actually two very different and important phenomena that are sort of driving a lot of the changes we're seeing. On the one hand, maybe on the more intuitive side, If there is a big spill of water on your kitchen counter and you use a big sponge to soak it up, that sponge soaks up a lot of water. A larger sponge could soak up more of that water. When you wring it out, it's going to produce more water, hopefully in your kitchen sink or something. In the case of the atmosphere, what this means is a warmer atmosphere can hold exponentially more water vapor. So the warmer atmosphere is acting like a larger and larger sponge. So if the ceiling on how much water you can absorb increases, well, if you wring it out, the ceiling on how intense the precipitation is going to be, which is the equivalent of wringing out the sponge, that's rising quickly in a warming climate. In fact, it rises at about 7% per degree centigrade or 3 or 4% per degree Fahrenheit of warming. So this is, that's like compound interest in a bank. So each 3 or 4% is slightly larger than the 3 or 4% before it because it's 3 or 4% per degree. It's compound growth. That's one piece of this. But the other side of it, so that explains why we get more extreme precipitation events, more intense atmospheric rivers, heavier downpours, just like the ones we've been seeing in California this week, actually. I mean, as we say this, there's another series of extreme precipitation events unfolding in California. But it also explains why, in large part, why we see more severe droughts and worse wildfires in a warming climate, which is because if you've got a much bigger sponge, but you don't have a lot more water to soak up, well, that sponge is going to demand more and more water from the landscape. And in the case of the warmer atmosphere, it's acting like a larger and larger sponge. When it is saturated, it can rain and snow more heavily. But when it's not saturated, it's going to drive potentially more intense evaporation, extracting more and more water out of bodies of water and out of the soil and out of plants. And so in doing, essentially it means that unless we get a lot more precipitation in a warming climate, which there's not really an indication that we will on average, and the rates of evaporation, or at least of potential evaporation, are more intense because the sponge increases in size, if you will, then we have land surface, soil, plants, things like that dry out faster and to a greater extent than they used to, more easily. So we have more rapid drying, we fall into droughts more easily and more severely, and the vegetation, fuel for potential wildfires, it dries out faster, and we get more intense and more extensive and faster moving wildfires as a result. So kind of in a nutshell, that expanding atmospheric sponge effect as temperatures rise explains a whole heck of a lot of what we've seen, around us in recent years, and a pretty big part of how we think things are going to continue to change. Doesn't explain 100%, but it's a good 80% of what's going on, I'd say.
That's really helpful because that really helps. I love the metaphor. It's visual for me and I can understand it better. And I haven't heard it put that way. It makes more sense why we have so many wildfire problems, because things are just, if that sponge is just pulling all that moisture out, especially in the Western US, the dry, all the trees, the plants, everything's just ready to burn and there's nothing really there to stop it. Calling all ski enthusiasts. Elevate your winter getaway with an all-inclusive experience at Club Med. The resorts in France, Switzerland, Italy, and Quebec offer a seamless blend of breathtaking ski adventures, locally inspired cuisine like fondue, and lively après-ski delights, all included in your package, so you can focus on conquering the slopes, indulging in the flavors, and creating unforgettable memories with your loved ones. Visit www.clubmed.us. Call 1-800-CLUB-MED or call your travel advisor to craft your ski dreams. To bring some other specificity to it as skiers and riders, the atmospheric rivers are getting more intense. I haven't actually heard that from anyone yet. And do you know, is there any way to add specifics to that, or how much more intense are these atmospheric rivers getting?
Well, this is a blend of sort of reading the tea leaves and reading between the lines a bit. There's a lot of peer-reviewed scientific research suggesting that atmospheric rivers will get more intense in a warming climate. And then there's also observational data from recent years that suggests that essentially that they already have. And that had been a little bit elusive until the last few years. You added a few more data points, and I think we've pretty much gotten there now in terms of seeing this in the real world. I think we'll see some more papers on this coming out in the next few years. But fundamentally, it's the same effect, and they're getting more intense at roughly the same rate, I would say, as that ceiling on how intense precipitation can become. So sort of that 7% per degree centigrade, 3 or 4% per degree Fahrenheit. And globally, at this point, we're right around 1.3, 1.4 degrees centigrade of global warming at this point. So we should be maybe right around 10%. So I would say at this point, studies vary where you are regionally, it's plus or minus, but a good rule of thumb is at this point in history, with about 1.3, 1.4 degrees centigrade of global mean warming so far, that things like atmospheric rivers and the most extreme precipitation events are probably about 10% more intense than they would have been the equivalent events in the 20th century. So that's actually pretty significant already. I mean, that's not a small thing. And the rate, by the way, of enhancement actually is higher for more extreme events. So that's sort of for a typical event. But if you're talking about a really high-end extreme precipitation or flood or drought event, it's probably more. It's more than 10%. So that one of the challenges in a warming climate is we see some of the largest fingerprints on the most extreme events. So the heavier the precipitation event you're talking about, the larger the contribution in relative terms of climate change to that event, which is a little bit counterintuitive, but there is some interesting science as to why that's the case. So for the moment, suffice it to say that I think a good rule of thumb at this point, in our warming history, is to assume that the typical precipitation event, if you're a downpour or downburst or something, it's probably about 10% more intense than it would have been. Now, if we double it again, double the amount of warming we've seen so far, it's going to be more like 20% more intense or more than that. So, all of a sudden, this is a pretty large additional increment, especially given that if you're talking about at watershed scales, right, you're aggregating that across the whole basin. And all of a sudden, that's a whole heck of a lot of extra water that we're talking about. And the same thing is true in reverse. So for the evaporative demand, by the way, the increasing thirstiness of this giant sponge, that too is probably 10 or so percent more intense than it used to be, and might be closer to 20 or more percent more intense in the future. So these things, these are not small numbers we're talking about.
And I love that you're able to put a number on it for us, because that makes so much sense to me that yes, these precipitation events, especially atmospheric rivers, are getting more intense. That we could say 10%, but maybe a big system is more than that, 15%. And then in the future, that might be up to 20% more intense than what we've seen before. And I was just looking up the numbers. I think what I saw, at least, and I'm curious if you know these numbers, somewhere around 31 atmospheric rivers hit the West Coast in the 2022-23 winter. And that is insane. And you could just quickly respond. Do you know those numbers? Is that about what you've heard?
Well, it was definitely in the dozens last year. I mean, last year was quite an extraordinary winter in California, so I don't doubt those numbers. The exact numbers depend a little bit on the algorithms you use to count them, but
Right.
no reason to doubt 31.
Yeah, but so that's insane. So you can see how we had a lot of extreme events all backed up together. Atmospheric river after atmospheric river. They may have been somewhere around 10% more strong than they usually are. And I love atmospheric rivers as a skier and rider. Yeah, sometimes they're warm, but in general, we just get such amazing, big, really snowpack building storms out of these things. And so I guess just to rewind a little bit, could you just tell what is an atmospheric river and what is their role in the West? Because I've heard numbers that huge percentages of our precipitation in the West Coast come from atmospheric rivers.
Yeah, well, atmospheric river is a formal meteorological term these days, and it refers to these meandering corridors of very concentrated atmospheric water vapor moving quickly in the column of air above your head. And they do somewhat resemble, hence the name, their terrestrial river cousins. If you look down on them from space, from a satellite or something, or from the International Space Stations, this literally does look like a meandering river, like a Mississippi in the sky. And in fact, they do carry an amount of water many times that of the Mississippi, an actual volume of water in vapor form. So these are not, these are not insignificant features. These are every bit as significant as their terrestrial cousins in terms of how much water they're moving. In fact, in a lot of cases, they move more water more quickly than some of the largest rivers on Earth do in liquid form. So it's
Wow.
no surprise then that these things can dump massive amounts of water if conditions are right. Now, just water being there in the atmosphere is not enough to create a big precipitation event. You still need that upward vertical motion to squeeze it out. In the Western US, a lot of the times, either the coastal mountains or the mountains further inland are the ones that do the heavy lifting. Literally, they force the air mass to rise. It's flowing out there over the Pacific, and then no barriers for thousands of miles, and then it hits the coast ranges or the Sierra Nevada or the Cascades or the Rockies, depending on which elevation tier you're talking about. And a lot of that moisture gets squeezed out by orographic lifting, which is really just a fancy term for saying that the air hits the mountain and it's forced to rise, cool, condense, and then precipitate in these winter storms. So, these atmospheric rivers, are hugely important in terms of water supply, broadly producing in a lot of places out west, like 30 to 50% of all the precipitation that occurs. But in certain places and
Wow.
in certain years, it can be like 70 or 80%.
Wow.
And in California specifically, atmospheric rivers make or break years. You either get a couple of extra big atmospheric rivers and it's a really super wet year. You miss out on just one or two of these atmospheric rivers, and you can actually be in a drought. So
Mm.
feast or famine, in California is largely thanks to, presence or absence of just a few atmospheric rivers each year. So it's kind of
Hmm.
on that razor's edge, and atmospheric rivers are the reason.
Thank you for that. If you were a diehard skier or snowboarder, where would you move to? Where would you live to maximize snowfall in the next 20 years?
I mean, I don't know. I know that there are folks who do sort of prioritize skiing above all else and sort of make that the primary consideration where you would live. I mean, I
You're
think
talking
really,
to him.
I think elevation is your best bet. I mean, as we were talking about
Mhm.
earlier, I mean, you buy a lot with elevation because, if you go high enough, and this is true anywhere really, you go
Mhm.
high enough and you're still on the below freezing side of the freezing line. So, imagine you're in a place like South Lake Tahoe where historically wintertime temperatures were frequently right around 32 degrees Fahrenheit. A couple of degrees of warming, now you're just on the wrong side of that line all the time. But imagine instead you're in a place where, winter temperatures are more often 20, 25 degrees Fahrenheit. You get that same 2, 3, 4 degrees of warming, you're still below 30 degrees, you're still well below that freezing line. And what you get with that is really, I mean, the most reliable indicator of temperature in a certain sense is elevation. You go up higher in the atmosphere, and except under very unusual circumstances, it always gets colder the higher you go. You can have a
Mhm.
temperature inversion that happens occasionally, but the global atmosphere on average, it gets colder as you go up pretty quickly. This is why you
So,
can have, skiing in near the tropics if you go high enough, right?
mhm.
Like you get a high enough elevation, you get that even at really low latitudes. So
so
elevation is really going
that's
to be the key thing.
so that's it. Yeah, so it makes sense. So which really would push people towards Utah, Colorado, places like that, where the base of the mountain can be as high as 8,000 feet. I think the bottom at Arapahoe Basin is 10,800 feet. So it might be a lot of California ski dirtbags living in Arapahoe Basin soon. So thank you for all that. And one thing that I think all of us skiers and riders want to know are these next three questions. Starting with, how far out can you realistically forecast the weather?
Yeah, it's a good question, and it depends on it actually is surprisingly case dependent. And
Mm.
sometimes we know that what we're predicting is very likely to be true, even sometimes a couple of weeks in advance. Other
Mm-hmm.
times we know that there's a lot of uncertainty. Like actually, as we're having this conversation right now, there's a potential for a very strong storm in California
Mm-hmm.
Sunday through Tuesday.
Oh,
And
please.
it does, by the way, actually look like it should be a pretty good snow producer after a winter of really kind of anemic snow producing events. But the key part that I'm talking about though is the fact that we don't know right now exactly the path that the slow is going to take. Is it going to sort of zoom up by the San Francisco Bay Area, or is it going to make landfall on the Central Coast? Is it going to produce a really big major windstorm along the coast? Is it going to lead to
Mm-hmm.
a major flood event in the LA basin? All of those things are possible, and I don't really know at this point. It's Thursday, and we're talking about something that's going to happen starting on Sunday.
Soon.
So it's very soon, and this is a high uncertainty situation. So it's an example of a case where we know that we don't know exactly what's going to happen, even though it's a very consequential forecast. Whereas there are other periods, in the past where it's dry today, it's dry next week, and it looks like it's going to be dry the following week. And we can pretty much say, yeah, that's probably going to be true. So part of it is recognizing that there are periods of good predictability and other periods of poor predictability. At the high ends, and the further out you go in the future, the more the prediction has to become probabilistic. So it's not like saying 2 weeks from Tuesday, there's going to be, 6 inches of snow between noon and 5 p.m. At 7,000 feet, near South Lake Tahoe. What it's saying is, there's an above average chance of a wetter than average pattern that'll be cooler than average, 2 weeks from now. That's the kind of statement you can make a couple weeks out. Whereas if we're talking about Sunday, this is a bit of an exception, but usually we can start to get specific about actually there might be a couple of feet of snow. Here's roughly where we think the snow line is going to be, and within plus or minus 3 to 6 hours, here's when the storm is probably going to start. So we can be more specific in space and time, the shorter the temporal window. And this is, by the way, the main difference between weather forecasts and climate projections. It's just an extreme version of this, where weather forecasts are what we call deterministic, specific in place and time. It's going to rain in San Francisco at noon on Tuesday, versus probabilistic, which is to say in the next 3 decades, we're going to see temperatures that are much warmer than the long-term average, and we may see increasingly wide swings between wet and dry. But I can't tell you if 2036 is going to be a wet year or a dry year. There's absolutely no way to know. I don't know if 2036 is going to be cooler or warmer than 2035, but what I do know is that 2036 is very likely to be a whole lot warmer than this year or any year in the 20th century, and that there's a pretty good chance that it'll be either a wet or a dry year rather than a near average year. So, but I don't know which it is, and so we can't be as specific.
So you're almost really saying that, but moving forward, on average, or it might be more likely that you see huge years, big snow years, and then really drought years. That's going to be more likely than seeing just a regular average year.
In some ways, yeah, that's probably what we'll start to see. I mean, we will see less snow on average, but the way that average comes to be might well be that we see a lot of years with almost zero, and then other years where we get these big snowstorms and these huge accumulations all in one fell swoop. The kind of temper that decrease in the average a little bit.
And that's what, again, coming back to, I feel like that's what we're seeing already. We don't really have average years anymore. It's either really big or really small. We don't get that middle of the road, which is much better as a skier and rider. You just want average because it's so much easier to plan your winter and plan your trips and plan your life. So you kind of mentioned this, but I'm just curious, how valuable do you think the monthly outlooks that National Weather Service puts out, or the 6 to 10 day, 8 to 14 day outlooks? How valuable do you think those are?
Again, it's kind of situation dependent. Sometimes we really do have a good handle on what's going to happen 6 or 10 or even 14 days out, at least in terms of tilts and the odds towards wet and dry. Monthly scale, the seasonal scale is tough. And we're at the point where usually we can get the sign of the temperature right. Part of it is cheating a little bit because on average, it's warmer than average most of the time. So that's usually the answer. But we're better at sort of these multi-month sort of temperature outlooks. But when it comes to precipitation, we're not so good. And there, almost all of the skill is very conditional, where unless there's like a strong El Nino or La Nina event in place, which does give us some hints, there isn't a whole lot of information. We're still not very good at seasonal predictions. I will say, though, that a lot of folks poo-pooed this winter. Like there was a tilt in the odds towards warmer and wetter than average conditions in a lot of the Southwest, including Central and Southern California, Central and Southern Sierra. And December certainly didn't look like that. January didn't start out like that. But now all of a sudden, it kind of looks like that prediction is going to end up being exactly right, because just over the next week, we're going to get a ton of water in Southern and Central California, Southern Sierra, Lower Colorado. It has been much warmer than average. That part has already been right. And so all of a sudden, I think we're going to end up right in that warmer than average for the season, and also wetter than average in the Southern and Central Sierra. So we might well see a season where precipitation percent of average is, pretty high, even above average, but the snowpack on April 1st might not look very, very good because, a decent amount of it fell as rain rather than snow or melted early. So, one of those examples of a seasonal forecast that a lot of folks assumed is not going to pan out, but maybe actually it is this year. And what does that tell us? It doesn't tell us that they're all good. Last year's was not good.
Hmm.
The last big El Nino, that was not a good predictive year either. But I do think that, we need to be thinking about them in the right context, right? Which is that they're never more than tilts in the odds. And even in a season with a prediction towards, wetter than average conditions, it can be dry and vice versa. But they're also not completely useless. I do wish they were better.
I love that you gave us that information because one of our most popular articles every year is when the National Weather Service first, usually it's in August or September, comes out with their winter predictions. It's essentially their 3-month outlook. And people lose their minds for those, and all the other companies that do weather come out with those, and people lose their minds from them. And I always try to say, hey, I think I talk to my editors, we should publish, a little bit of a warning that, hey, these are just their best guesses, and I really don't put a ton of weight into them. Sounds like you don't put a ton either, but I do think they're valuable. So I guess my final questions here is, how much weight do you think skiers and riders should put in those seasonal forecasts? And in general, I say, we can forecast pretty well about 3 days out on average. And that's sort of where when I talk to people to temper their expectations, I say the 3-day thing. So yeah, so I'm curious what you think about my 3-day ideology, and how skiers and riders should think about the winter outlooks that come out in the fall.
I mean, in general, we have really good weather forecasts these days in most conditions out to 5 to 7 days. I think the challenges with ski forecasts specifically is that you're very sensitive to the details in terms of storm trajectories and freezing lines. Like you can be right about where a storm is, within couple hundred miles. You can be right about, the temperature within 2 or 3 degrees and still have a complete, snow forecast bust if it's a couple degrees warmer or colder, or if the storm is a couple hundred. So in other respects, that's not quite so important, but in that particular context, maybe it's a little bit shorter than the window that we have pretty good weather forecasts, in other settings. Because if you really got to get the snow line right, that can be tricky until a few days in advance. In terms of the seasonal, I mean, I think that, as I mentioned, you have to think about how they're designed scientifically and how you would evaluate them. You can't even really assess, for example, whether a particular season's outlook was a bust or successful on the basis of that single year, because, it was only saying, for example, for this year, that there's about a 1/3 tilt in the odds, towards about 1/3 likelier that it would be better than average than usual, and 2/3 likelier than usual that it would be warmer than average. So what you would actually have to do is look at dozens of similar years and compare all of the forecasts across all of those years. And if you got it right about 2/3 of the time, that would tell you that you probably were onto something. But in any given year, it's kind of like trying to determine if you got a weighted dice, right? Like one roll of dice, I mean, who knows? How would you possibly know? But if you rolled it 100 times and you started, coming up snake eyes half the time, you might get a little suspicious. So that's sort of a similar analogy. Is you can really only evaluate the seasonal predictions over many, many years. And people like to think, oh, this year's was they either nailed it this year or it was a bust. But really, we can't make either of those claims on the basis of a single year. We have to go back in time, and which is difficult because the climate is changing. We don't have dozens of years like this one to look back on. So it's tricky.
2 great takeaways. One, I love that you say, we can forecast the weather pretty well 5 to 7 days out. And then 2 is seasonal forecasts probably aren't great right now, but they will be in 100 years. So stick around. I like that.
Maybe we'll see.
Yeah. And even that is a maybe. So I guess my one final question would be, I just saw in some of your literature, you talking about a California mega flood. And I don't even know where to start with this question, but can you tell us more?
Yeah, well, all this comes back to the reality that we know that California is actually quite a flood vulnerable part of the country, more so than I think a lot of folks who live there realize. There's a long history of very extreme flood events in the paleoclimate record. So we look at river sediments and lake sediment deposits, things like that. About 5 to 10 times per millennium, so every 100 to 200 years, there comes this huge flood deposit that greatly exceeds anything that we've seen in the last century or so. So that suggests that this is a part of the world that is, at least on geological timescales, quite susceptible to super big flood events. And then we have, what happened in 1862, which is probably the most recent analog for an event like this. The Great Flood of 1862 in California, which inundated much of the Central Valley and most of the Southern California coastal plain, where millions of people now live in Los Angeles and Orange counties. A modern repeat of this would be sort of a disaster of epic proportions. And this is part of what we've pursued academically and scientifically in the arc storm scenarios. I was involved with designing the arc storm 2.0 scenario, which is an updated version of the original one from a decade ago that includes things about climate change in it.
And what is the arc storm?
It's really just a multi-week extreme storm scenario for California that would produce widespread and catastrophic flooding. Really, it's a 3 to 4 week sequence of over a dozen powerful atmospheric rivers. And we know that can occur. That's sort of, if there is going to be a really big flood in California, that's kind of how it's going to happen. That's the main mechanism. And so the basic idea is we game this out, we create a scenario, we look at what would actually happen in the state if and when this occurs. And by the way, it is a matter of when, really, rather than if. And what it would look like in terms of flooding and what we can do to mitigate those risks. Now, we did find that in a warming climate already, that although we haven't seen one of these events since the 1860s, that the risk has probably already doubled quietly in the background while we were so preoccupied with drought and wildfire and less
earthquakes.
Snow. Earthquakes, everything else. This is something that sort of snuck up on us, and that with continued warming, that the risk might double again, which doesn't sound like a lot. Still a rare event, something that might happen. If it was originally something that happened every 100 years, now it's maybe something that happens every 50 years. But then if it doubles again, then it's something that happens maybe every 25 years, and all of a sudden, that goes from something that the average person would never experience to something that most of us will see more than once.
Wow.
In our lifetime. So that's a real consideration.
And how well set up is California to handle that?
Well, it's another tricky one. In some ways, obviously, we're much better set up than we were in 1862. We have flood control, we have levees, we have emergency management and telecommunications and things that we didn't have back then. But on the other hand, we have millions of people living in floodplains where no one lived in 1862. We have a lot of people living downstream of these big reservoirs and these dams and these levees that may in some cases, are robust, and in some cases are not so robust. And so we're still working on sort of assessing really what the consequences would be with a contemporary recurrence of an arc storm level event. Active research still underway on that front. So our hope is that we academically get the answer before we find out in the real world, because then we can maybe do something about it before we have to sort of bear witness to the consequences. So, we're hoping that we can get that work done before the real one actually hits.
God, and what would snowfall at high elevations look like in an event like that?
We actually looked at that specifically in some of our own research into this. The answer is it's in the dozens of feet of snow.
Oh my God!
But let me just be more specific about it. So again, this is a 4-week scenario. So it's a 30-day, or 28-day, I suppose, scenario. And we know that in the warmer future scenario, of course, the snow line is higher up the mountain. So you get a lot more rain at 4, 5, 6, even 7,000 feet, but you're still getting at 8 or 9,000 feet, you're still just getting this massive amount of, Sierra cement. You're still below the freezing line most of the time. And so you're getting most of that precipitation at very high elevations as snow. And I'm just pulling up the actual figures from this because I remember being surprised by the actual numbers.
I'm excited. I want a drum roll.
Yeah, right. All right. So what we see is that there is in the ARC future event, which is this warmer future one. We have an equivalent one for ARC historical, but I'll go for the future one because it's an even larger number at super high elevations. We sort of have this dipole pattern of snow water equivalent changes. So where there's a huge decrease, like a 50 or more % decrease in the snow water equivalent for the future scenario at lower elevations. So we're talking about almost getting rid of all the snow below 6,500 feet completely. But at the highest elevations, we're talking like above about 3,000 meters. So I'm just doing the math in my head since I am ultimately an American scientist. That's like right around 9,500, 10,000 feet, I think. Let me just...
3,000 meters?
It's like 9,800 feet elevation. Yeah. So we're really talking about like the top of the chairlift at Heavenly or something like that. Up there, in this ARC future scenario, we found a maximum of 10.4 meters of accumulated snowfall.
Whoa.
So again, doing that metric conversion, let's see, that's something I think like 33 feet.
Yeah, that's my math.
And that's or 34 feet, somewhere around there. And again, that's not the amount of snow that fell necessarily. That's the amount that actually like accumulated on the ground. So there's some melting involved, but that's the net number. So on some mountain peak in the Sierra, we're talking like 30 to 40 feet of snow in 4 weeks from this sort of event. Now, granted, you might have to be up at 10,000 feet, but that would probably do a good job of burying the chairlift, I would imagine.
I mean, and that's what I'm thinking. I'm thinking repercussions because I just did the math. 34 feet is about 408 inches of snow. And so a lot of times we like to think about in inches is 400 inches is a good annual snow for any location. So to get that in 1 month, I mean,
3 to 4 weeks.
And if it was hitting a ski resort, I mean, I'm talking about like people trapped in their homes, avalanches probably taking out entire buildings or villages.
Well, and the dramatic part, the dramatic part in this scenario, right, is that's what you might be getting up at 10,000 feet, but down at 6,000 or 7,000 feet, you just would have this massive flooding because most of that would be falling as rain. So you'd have this gradient up the mountain, right, where there's be this crushing amount of snow at extremely high elevations and really severe flooding once you got below the snow line. And so a real mess.
Oh, and understanding how avalanches work, even if the snow was up high, it would be able to avalanche quite low with that much mass. And so you'd be getting avalanches coming down into the the rain zone and just taking things. I mean, this is the kind of thing that would eliminate multiple ski resorts. I mean, if that happened specifically in Lake Tahoe and maybe snow levels were somewhere around 8,000 feet, that could potentially eliminate our 18 ski resorts in one fell swoop.
Granted, this is a particularly extreme scenario, right? So this is by design like an extreme event, but it's something that we see as is as plausible and something we'll have to consider. Where it's a lot of water no matter how you slice that. It's a different problem if it's liquid water below the snow line versus solid water above the snow line, and you do have problems either way.
And you're talking about this being somewhere around a 100-year event, but it hasn't happened since 1862. So we're a little bit overdue potentially.
Well, I actually dislike the term overdue because it suggests that there's some schedule. And really, this doesn't occur on like a recurring, when we say 100-year event, we don't necessarily mean that it occurs on some, particular 100-year cycle. It just means that in any given year, there's about a 1% chance. So it means that, it could happen next year. It might not happen for 60 years. But in a warming climate, those odds are going up.
Unbelievable numbers. Thank you so much, Daniel. Daniel, that's all I've got for you today. Thank you so much. Do you have any other thoughts that you'd like to share here at the end of the show?
I think we covered a lot of ground, but I think that's it. Thank you.
We kicked some butt. You're very welcome. Thank you so much, Daniel. I greatly appreciate your time. Let's stay in touch. I'd love to have you back. I'd love to talk about the California, or I guess the all over the place medieval climactic anomaly and more. There's so much. You have so much good information in your brain. Thank you again. Thank you so much for listening to the Snowbrains podcast. If you liked this podcast, please share with your friends and family, and please subscribe. To find out more about Snowbrains, please visit us at snowbrains.com. You can also find us on Instagram, Twitter, and Facebook at Snowbrains. This episode of the Snowbrains podcast is brought to you by Club Med. Experience the ultimate ski getaway at Club Med, where every detail is meticulously taken care of. With their all-inclusive packages, you can focus on what you love most, skiing. With over 20 plus mountain resorts in the Alps, Japan, and Canada, enjoy world-class slopes, refreshing après-ski activities, and gourmet meals, all while knowing your accommodations, lift tickets, and childcare are all included. Let Club Med take the worry out of your ski vacation so you can simply relax and enjoy the ride. Visit www.clubmed.us. Call 1-800-CLUB-MED or call your travel advisor to plan your stress-free ski escape. This episode of the Snowbrains podcast was edited by Jared White and Ben Hout. Music by Chad Crouch. I'm your host, producer, and creator, Miles Clark.